Now friends, this is a numerical problem based on the shear force and the bending moment diagram. Here, this is an overhanging beam and this is the concentrated load of intensity 20 kN per meter. And there is a point load acting at this point E, and these are two supports, and we have to draw the shear force and bending moment diagram. So the first equation is that we have to suppose that the reaction at the point A is acting in vertically upward direction RA, and reaction at B is also acting in vertically upward direction RB. Now we know that RA plus RB is equal to the net vertical load acting over this beam. So the net vertical load will be equal to this 100 kilonewton, okay, plus this in load intensity 20 and multiplied by the total span over which this UDL is acting, which will give us 20 into this value, that is 5 plus 5 will give us 10. So into 10. So it will give us how much? 300. So 300 kilonewton is the RA plus RB. Now we know that summation of moment about point A can be taken as 0. So because of this RB, there will be a movement about this point A which will go in anti-clockwise direction, having the magnitude RB into this distance 5 plus 5 is equal to 10 about this point A, which will go in anti-clockwise direction. And because of this load of 100 kilonewton, there will be a movement about the point A going in clockwise direction, okay, so denoted by negative sign, having magnitude 100 into this distance 4 plus 5 plus 5. It will give us how much? 40. And because of this UDL, okay, this portion which is lying between the A and D, there will be a moment of magnitude minus 20 into, that is the intensity of this UDL, minus 20 into this distance 5 meter, okay, and it will act here in the middle of the AD, that is at a distance of 2.5 meter from the point A, okay. So multiplying it with 2.5, okay, so it will give us movement rotation in clockwise direction about the point A. Now because of this load acting which is lying between the points C and A, there will be a movement which will rotate the beam element CA in anti-clockwise direction. So anti-clockwise is taken as positive, and because of this loading between point C and A, there will be a movement of magnitude 20, that is the intensity of this load, into this span of 5 meter between the point C and A, and it will act at a distance of 2.5 meter from the point A, okay, here, because it will act at a distance which is equal to half of the length of CA, that is half of the 5, which is equal to 2.5. so it will act somewhere here at a distance of 2.5 from this point A, okay, so that's why we will multiply it with 2.5 and it will act in anti-clockwise direction. Now when you solve this, what you will get, you will put this thing, whole equation, to 0, then you will get RB is equal to how much? Is equal to 140, and RA is equal to 160. Using this equation and this equation, you can find this RA and RB by substituting the value of RB obtained from this equation into this. You can get the RA, okay, it will come in kilonewton. Now we will draw the bending shear force diagram. Now friends, we will calculate the shear force at the point C, A, D, B and E. We will calculate the shear force on the left side of the point A and on the right side of the point A, and similarly we will do it for the point B also, on the left side of the point B and on the right side of the point B, and similarly on the left side of the point A, E, and right side of the point E. Why? Because at these locations A, B and E, there is point load acting, and here reactions are acting at point A and B. That's why on the left side and on the right side we have to calculate the shear force at point A, B and E. Whereas at the point C and D there is no point load acting. That's why we will only calculate the shear force at the point D and the shear force at the point C directly. So shear force at the C we will calculate. For that we have to construct a section passing through this point C. You can see that if you look on the left side of this section, you can see that there is nothing lying. That's why shear force at the point C is 0. Now we will calculate the shear force on the left side of the point A. For that we have to construct a section passing through passing through the left side of the point A. Suppose this is the section which is passing through the left side of the point A. The point A is lying somewhere, is this point, okay? This is the point A actually. So on the left side of this section, you can see that this portion of the UDL is contributing toward the shear force, and the magnitude of that will be equal to the intensity of this load, which is equal to 20, and it is acting over a span of 5 meter, which is lying between the section XX and point C. So, and it will have a sign, negative sign, because using this sign convention we can have the negative sign, because this is the section XX, and if a load is acting on the LHS of this section XX and going in downward, then it can be treated as negative. Similarly, this is the section XX, and because of this UDL there will be a load acting at the center which will go in the downward direction, so that's why treated as negative. So this will give us minus 100 kilonewton. Now shear force on the right side of the point A we will calculate. For that we have to construct again a section on the right side of the point A. So this is a section constructed on the right side of the point A. Now looking on the left side of this section, this portion of the UDL is contributing to a shear force of magnitude minus 20 into 5 using this sign convention, and this reaction RA is contributing toward a shear force of how much? The magnitude of this reaction is 160, so it will contribute to a positive shear force of 160 kilonewton using this sign convention. So it will give us how much? It will give us 60 kilonewton. Okay. Now shear force at the point D we will calculate. For that we have to construct a section passing through the point D. So suppose this is the section which is passing through the point D. Now this is the section XX. Now looking on the left side of this section, you can see that because this UDL is lying completely on the left side of this section XX, so because of this UDL there will be a shear force of 20 into the length of this UDL, that is 5 plus 5 is 10, and it will create a negative shear force over this section XX using this sign convention, and this reaction RA will contribute toward a positive shear force of magnitude 160 kilonewton, and this will give us shear force at the point D as minus 40 kilonewton. Now we will calculate the shear force on the left side of the point B. So for that we have to construct again a section on the left side of the point B. So this is a section constructed here on the left side of the point B. Now looking on the left side of the section, or on the right side you can look, because looking on the left side is easier for us, so we can look on the left side of the section. So this complete UDL contributing toward 20 into 10 kilonewton of shear force about this section XX, and this reaction RA is contributing toward 160. Okay, so this will again give us 40 kilonewton. Now we will calculate shear force on the right side of the point B. So construct a section on the right side of the point B. Now on the right side of the point B, now you can look on the left side of the section also. I am looking here on the right side. Okay, both the things will give the same result. So because on the right side of the section only this force is accounting for shear force, this point load, and this is creating a positive shear force using this sign convention. Why? Because this force is lying on the LHS of this section and going downward. Similarly, if a force is lying, if a load is lying on the RHS of a section and going in vertically downward direction, it is treated as positive. Similar is the case here. It is lying in the RHS of this section and going vertically downward direction, so it will be treated as positive and give us 100 kilonewton. And shear force on the right side of the point E will also be 100 kilonewton. You can do it by constructing a section here on the left side of the point E, and looking on the right side of the section, you can see that this force is contributing toward a shear force of 100 kilonewton, and shear force at the right side of the point E is 0 because the beam terminates on the right side of the point E. Now we will draw the shear force diagram. So these points are projected, that C is projected here, A is projected here. Similarly you can do for other points. Now shear force at the point C is 0, so making a cross here, and shear force on the left side of the point A is minus 100 kilonewton. So all the things which are negative will lie below this line. So minus 100 kilonewton suppose lie here. Okay, so shear force at the point A is minus 100 kilonewton on the left side. So I will write here 100 kilonewton. Okay, and shear force on the right side of the point A is 60 kilonewton. So it is again going to 60 kilonewton, suppose lie here 60 on the right side of the point A. And shear force at the point D is minus 40 kilonewton. So it is again going to minus, that is minus 40 kilonewton on the at the point D, and shear force on the left side of the point B is minus 40, so we'll lie in same level minus 40, and shear force on the right side of the point B is 100 kilonewton, so it is again increasing to 100 kilonewton at the point B. So we'll make a cross here at a distance of 100 kilonewton above the point B, and shear force on the left side of the point E is 100 kilonewtons. At the same level it will lie, and shear force on the right side of the point is 0, so making a cross here. So joining the first point with the second, first point was this and second point was this and drawn, and second was joined with the third like this. Why we have joined first point with the second with the inclined line? Because there is a UDL line between the point C and A, and there is a point load in the form of reaction R is lying in the point A. That's why this point is joined with this point with a vertical line. And again we will join this point with the point D, that is point with the next point with the inclined line, because there is a UDL line between the point A and D, and this point is joined with the next point, that is this was our next point. We have drawn this next point with a straight horizontal line, because there is no load acting between the point D and E, and there is reaction RB acting. That's why we will again draw a vertical line to join the next point, and the last 2 points these are joined with a straight horizontal line, because there is no load line between the point B and E, and again there is a vertical line will join because there is a point load line at this point E. So this is our shear force diagram. Now shear force diagram will look like this, and this is negative loop, and this is positive, this is negative area, and this is positive area of the shear force diagram. Now friends, let us find out the point at which the shear force is going 0. So shear force is going 0 at this point. Suppose this point is named as K. Okay. Now friends, I have to find out the location of this point. So consider these two triangles, this triangle and this triangle. These are the similar triangles. Now suppose that the length, we know that for this triangle the height is suppose y1 and this base is x1, and for this triangle the height is suppose y2 and this base is x2. Now we know that according to the property of this similar triangle, if these two triangles are similar triangles, then y1 by x1 is equal to y2 by x2. We all know that, and we know that x1 plus x2 is equal to 5 meter. So x1 plus x2 is equal to AD, that is the distance between A and D, and it is equal to 5 meter. Okay. Now friends, if we substitute the value of x1 is equal to 5 minus x2 in this expression, and the value of y1 is 60 here from this shear force diagram, and x1 is substituted at 5 minus x2, and y2 is taken here as 40, okay, from this triangle, and x2 is substituted as x2 here, then you can find that the x2 will come out from this equation as 2 meter, and x1 will come out to be 3 meter. Okay, so the point where the shear force is becoming 0 will lie at a distance of this, if the x1 is 3, okay, and we know that this distance between C and A, this point is 5 meter, then the shear force becomes 0 at a point which lie at a distance of 5 plus 3 is equal to 8 meter from the point C. Okay, so at x is equal to 8 meter from the point C, the shear force is equal to 0. Okay, now we will draw the bending moment diagram, and we will calculate the bending moment at various points. Now friends, we will calculate the bending moment at the point C, A, D, B, E. We do not have to calculate on the left side of the point C and right side of the point C. Similarly, we have done for the point A, B and E in the previous case where we have calculated the shear force, because there is no concentrated movement acting over this simply supported beam, overhanging beam. Okay, so we will directly calculate the bending moment at the point C, A, D, B and E. Now friends, bending moment at the point C. For that we have to construct a section passing through this point C, and we know that beam terminated at the point C, and on the LHS of this section nothing is lying, so bending moment at the point C is 0. Now bending moment at the point A, for that we have to construct a section passing through the point A. Now if you look on the left side of this section, you can see that because of this UDL there will be a bending moment of magnitude equal to the intensity of this UDL is 20 and the distance over which it is acting is 5 meter, and the distance at which it will act will be equal to 5 divided by 2. Okay, 5 divided by 2, that is at the half of this distance CA it will act, and it will cause a hogging bending movement by this kind sign convention. You can see this. Okay, now this will give us a bending moment of magnitude minus 250, okay, kilonewton meter. The unit I am not writing, you should understand this, that this is kilonewton meter. Now bending moment at the point D you can find out by constructing a section at the point D. Now I am not constructing a section, so here I will do this problem without constructing section. Now I think you have become familiar with the section process. Now I will do this without constructing the section. So looking on the left side of the point D, you can see that this whole UDL is contributing toward a bending moment at the point D of the magnitude, that is minus 20 into the length of this UDL. 5 plus 5 is equal to 10, and it will act at a distance of 5 meter from the point D, that is at the exactly midpoint of this span CD, which is equal to 5 meter. So, and because of this reaction which is acting at the point A, there will be a bending moment of positive nature, that is sagging bending movement, and it will have a magnitude of RA into this distance 5. So it will give us 160 into 5, this distance 5. Okay, so it will give us the bending moment at the point D as minus 200. Now bending moment at the point B we will calculate. For that we have to construct a section here. Sorry, you don't need to construct a section. Directly look on the right side of the point B. This force is causing a bending movement which is hogging in nature of the magnitude minus 100 into the distance, this distance 4 between the point E and B, and using this sign convention you can see that this force is creating hogging similar to this case, and because of it will give us how much bending moment? It will give us minus 400 kilonewton meter, and bending moment at the point E is 0, because if you construct a section here on the passing through the point E and look on the right side of the section, nothing is line, that's why bending moment at the point E is 0, and bending moment at the distance x is equal to 8, where the shear force is becoming 0. We have already calculated this distance, that at a distance of 8 meter from the point C, the shear force is becoming 0 at the point K. So we have to construct a section here passing through the point K. Okay, and it is at a distance of 8 meter. This section is at a distance of 8 meter from here, the point C. Okay, now friends, because of this UDL which is lying between the point C and this section XX, there will be a moment of magnitude 20, the intensity of this UDL into the span, that is 8 meter, and it will act at a distance of 8 divided by 2, that is 4 meter. Okay, and it will create a hogging bending moment. That's why negative sign is taken using this sign convention, and this force, that is RA, acting at the point A, will cause a bending moment of magnitude positive in nature using this sign convention of magnitude, that is the magnitude of RA is equal to 160 into the distance between this RA and this section XX is how much? This is 3, because the distance between the point A and the point K at which this section XX lying is 3. We have already calculated. So this distance between the RA and the section XX is 3. Okay, so in multiplying it with 3, we will get the maximum value of the bending moment as how much? You can calculate yourself as minus 160 I will get. Now friends, we will draw the bending moment diagram. Now friends, see this bending moment at the point C is 0, so we can cross here. Bending moment at the point A is minus 250, so minus 250 will lie somewhere here, suppose below the point A, minus 250. Okay, and bending moment at the point D is minus 200, so minus 200 will lie suppose somewhere here. Okay, and bending moment at a distance of x is equal to 8 meter is equal to minus 160, that is bending moment at K, where shear force is 0, which is lying at a distance of 8 meters from point C, this point, it's equal to how much? 160. So 160 will lie somewhere here, minus 160. This is minus 160 below the point K. Now bending moment at the point B is how much? It is 400. Minus 400 will lie somewhere here, suppose, and bending moment at E is 0. Now joining first point with the second, with these 2 points will be joined with a parabola, because there is a UDL line between the point C and A. Now parabola can go either way, like this or like this. Okay, so which parabola to choose? The question arises. Okay, so we will choose this parabola. Why? Let us see this. Now friends, see this. Between the point C and A, between these 2 points, shear force is increasing, okay, in negative direction. That's why the slope of the shear force bending moment diagram must also increase. See this. We know that shear force is equal to how much? Shear force is equal to dm by dx. That is, shear force is equal to the slope of the bending moment diagram. This is the slope of the bending moment diagram. As we know that shear force increase, then the slope must also increase. So if we take this slope, this type of curve, then it indicates an increasing slope in this direction as we move from C to A, because from C to A shear force is also increasing, and hence the bending moment diagram slope must also increase. See here how it is increasing. Suppose this is the distance dx, okay, then if this is the distance dx, then this will be our dm. Now the same length element dx, okay, is drawn here. Suppose dx is drawn here of the same length. This is the dx drawn here. Now dm will increase. The dm is for the same length of dx is this dm will correspond to the same length of dx. So dm is increasing as we go from C to A. That is, the slope is increasing. That is why we are choosing this parabola. Okay. Now friend, bending moment at the point K we have already calculated that minus 160. So joining this point with this this parabola, that is decreasing parabola, that is decreasing slope parabola. Why? Because between the point A and K the shear force is decreasing, so the slope of the bending moment diagram must also decrease. You can see the slope like this. Okay, that I have already concluded why I have chosen this type of curve. Now friends, join these 2 points with a increasing parabola, with increasing slope parabola. Why? Because between the point K and D the shear force is increasing, so increasing parabola will go like this. Okay, and between the point D and B we know that shear force diagram is a horizontal line. That's why these 2 points must be joined with an inclined line, a straight line. And between the point B and E the shear force diagram is a straight horizontal line. That's why the bending moment diagram will be a straight inclined line. So this is our bending moment diagram. So these whole area is